Yes. So now we are going to start today's session. And once again, good evening, all of you. Many participant has joined us. Today we are going to discuss about finite difference method, and this approach will help you in many ways, not only in ODE but PDE. And along with, I will let you know that some of the methods, or like just like forward or backward, will be seems to be similar as you can say Euler forward and Euler backward. Okay. And there will be three type. One is forward, backward, and central. So how these will can be developed, and then after how we can use. And I tried to present different examples for the same. So first I would like to share my screen, and then we will start. So you can see this is the screen, and my desktop is visible to all of you.
Yes, sir.
Great. So you can see, you can follow from the book which I shared with you, B.S. Grewal, Numerical Methods. Okay. And I think the page number is 480. And you can find here finite difference method. So in this method, the derivative appearing in the differential equation and the boundary conditions are replaced by their finite difference approximation, and the resulting linear system of equations are solved by any standard procedure. So how this method can be developed and how we can are using. Okay, just at the overview. The roots of the values of the required solution at the pivotal points. So here is the finite difference approximations to the various derivatives are derived as under. You can see if yx and its derivative are single valued continuous function for x, then by Taylor series we have these two equations, equation number 1 and equation number 2. But from the equation number 1, we can write it as y dash x is equal to 1 upon h yx plus h minus yx minus s by 2 y double dash. Okay, and then further you can rewrite as y dash x is equal to 1 upon h yx plus h minus yx plus oh. So this is the forward difference approximation. Okay. And similarly, we can have the from the equation number 2, you can see y dash x is equal to 1 upon h yx minus yx plus h plus oh. Okay. So the order of both we have is error is h. Okay. So this is the order of error of the order for both the equations. And if you will subtract the second equation from the first, then we can have y dash x is equal to 1 upon 2h yx plus h minus yx minus h plus oh square. So this is the central difference approximation for y dash x, and with an error of order is h square. Okay, and from these you can easily extend for second order, third order, and fifth order, whatever. You can see here are the equation number 3, 4, 5, and 6. Okay, third order, fourth order, fifth order. Okay, and so on. You can use for any kind of order. So only this information is not sufficient for us. Okay, for the understanding, it's okay, but for the implementation, this is not sufficient for us. So what do we do? I prepared these these three files, but after this session, I will combine all these three files, then I will share with you. Okay, so these three forward, backward, and central are very important. So from where I should start? Okay, see here, we have dy upon dx is equal to fxy. Okay, and fxy is some function. So what is finite difference? Say this is t naught, and here is tn. This point is ti. This point is ti, and this point is ti minus 1, and this point is ti plus 1. Okay, and here is some like graph. So at this point we have y I minus 1, and here is y I, and at this place we have y plus 1. Okay, so the part from when you will choosing from ti minus 1 to ti, okay, for this interval. So this will be the when you have the interval t, and also the difference between these consecutive point we have is h. Okay, so the entire interval we will divide in equal length, or you can say h is equal to dx, doesn't matter. Okay, so when you will choose dy upon dx, dy upon dt is approximate to this one, yi minus yi minus 1 upon h, or you will have this one, dy upon dt, you will have yi plus 1 minus yi upon h, or you can have the interval from ti minus 1 to ti plus 1. Three cases are there. Okay, so in this case you will have dy upon dt will be approximate to, now corresponding to the point ti minus 1 and ti plus 1. The total length of the interval we have is 2h, and the values are yi plus 1 minus yi minus 1 upon 2h. Okay, so we have these three cases, and from these three cases the first one is backward, this one is forward, and this one is central. Okay, and from these three expressions we will write the equations in iterative format, and then we can easily implement for using this finite difference method. Okay, so all these will be related to ODE. Scroll down. Okay, yes. So here you can see we are using backward difference. For this differential equation, we are using backward difference. Okay, and this is the condition which we are given, y0 is equal to y0. Okay, and here is ti, or you can take at this place tn, this will be tn plus 1, and here is tn minus 1. And if you have this function, so if you are using backward, then here is yn and here is yn minus 1. Okay, and the difference between these 2 points is h. So dy upon dt will be equal to yn minus yn minus 1 upon h. When h approaches to 0, when approaches to 0, the point which you will choose on the curve will become tangent. Okay, and will be equal to dy upon dt. Okay, so that will be yn minus 1 upon h, and we want to compute at this point, and the right hand side will become minus kyn. This part is dy upon dt, which will be equal to yn minus 1 upon h. Okay, and right hand side we want to compute at this point, to get this value at this point, minus kyn. And what is h? H is the step size, this one. You will simplify this equation number 2 and can be written as in this form. After simplifying this equation, you will have yn is equal to 1 upon 1 plus kh yn minus 1. Now we can easily use this equation to write the MATLAB program and apply the initial condition. Okay, so this is the initial condition, and yn can be computed for n equal to 1, 2, 3 and so on to get the result, and n is the total number of the steps. Okay, now come to the MATLAB for the implementation, and this is the backward difference. Okay, close all these files, and yes, you can see the same content are here. We are choosing the example dy upon dt is equal to minus ky, y0 is equal to 1 is the initial condition, and we can easily convert this equation by using the expression dy upon dt will be equal to yn minus 1 upon h is equal to minus kyn. Okay, and we will rearranging the same. Yn will be equal to this expression, yn is equal to 1 upon 1 plus kh into yn minus 1. Now you can easily implement in the MATLAB syntax. You can choose k is any parameter, and you can choose any value, some constant. So we are choosing here k is 0.1, and the initial value is y0 is equal to 1. T, the total time you can choose 10. Okay, this is the total time. So the total time is 10. Okay, so the interval we have is from 0 to 10. Okay, and the number of steps we are taking at this place 1000. So when you will choose h is equal to t upon n, you will have the step size. This is the value of h. Okay. And according to the above, we need to discretize to the domain, time domain, and then the same we will get the value corresponding to each iteration. So first we have the line space we are taking at this place 0 to t. T is 10. Okay, the interval is 0 to 10. And these are the number of points, n plus 1. Okay, so n plus 1 will be the number of points. Then what we do, the next step is same as we do in the old examples. C at this place. And you will have the problem always at this place. So after discretized time domain, we will initialize for the solution and using the zeros function. Okay, and the length of t and y must be equal as you know. So this is the initial condition, and one is the index. Y1 is equal to y0. Okay, and after that we are using backward difference approximation, which is this is the same as we draw in the above. Yn plus 1 is equal to yn and 1 upon k h. This is the same as we have. Once again, you can see here, you can see yn is equal to 1 k plus h yn minus 1. But here, see the difference. Yn plus 1 is equal to yn 1 upon k plus kh. Okay. Here is the problem. You will have the problem at this stage always. So can you please explain why we are taking at this place yn plus 1? Why we are not taking here is yn, but we are taking here yn plus 1. Why? Anyone please? Anyone please?
If we go with n plus 1, the loop will be test condition fail, so it will be come out from the loop.
Pardon?
Sir, initial value is 1 in the array script. So yn plus 1 is y2 and yn is y1. Y0 doesn't exist.
Y0 does not exist. Okay. Can I write in this way?
Actually, sir, because our n is equal to 1, we have already given one value. That is y of 1 is equal to y0. So we have to start from y2.
If I write the same statement in this way, then what should I do?
We have to start from n equals to 2.
N equal to 2.
Yes, sir. Yes, sir.
Why?
Because yn minus 1 means y0. And y0, it has no value in MATLAB.
See the index. See the index. Y1. This value will be used at this place. Okay. That's why. You are correct. We can take at this place 2. Okay. And some of the problem which I saw is related to the implementation of this for loop. That's why I was asking this question. Okay. So either you can start, you can use in this way, or if you want to start from 1, is it okay? We start from n equal to 2. Is it okay? Now it is correct?
2 minus 1, 1.
Yes,
Okay, correct.
Is it correct? Okay.
Then where is the incrementing of n value, sir?
Okay, we will run the code and then see what happened. Is it working? And if I make at this place 1, and then here was n plus 1, and here is this value. Okay, and then there is difference in the graph. What is the error?
Sir, n plus 1 value is missing in previous case.
Yes, you are correct. In the previous case, we changed only this one, but here we need plus 1 also. Now we have the same graph. Okay. So when you are applying the for loop, okay, what is the initial condition and what is the index you are using for the same? Okay, you need to initialize from this place, and the number of points which you generate at this place, all those must be same. Okay, all these points must pass at this place. Then your coding part will be correct. And now it is fine. And you can use also the grid on. Okay. Similarly, we have one more example. Okay. This is also the similar, but the way of writing the code is a little bit different. Yes, only at this place we change. The second equation is the same. Okay. So only this part we introduce only Tn is equal to n minus 1 into h. At this place we introduce iteration for the same. In the previous example, we use line space, but here we are using a loop for both the parameters. Okay, only this is the difference, but the example is same. We did not change the example. And here we write the user defined function, and then we use for the numerical part, we are using this file. Okay, yes. So there are 3 ways to write the program. One is this also. By using the function, you can write the code, finite difference ODE. In this way, you can write also. And this is the line space. Other thing will be same. Other parts are same. You can see. Okay. So this is we are using also add space function, and when you will execute, you will have the same graph. And in the other way to write the program is user defined function. Okay. So here is the function which we create for this method. Okay. Backward difference approximation. Okay. And these are the same part, and just we convert in this function. And for the numerical result, we are using these parameters, and at this place we call the user defined function, and then we are plot the graph. So other things are same. You can present in a different way. Just you need to understand the syntax, how you can present these methods. So this is all about backward difference. Now we have any question, please? Any question related to this method? If you have.
Excuse me, sir.
Yes, sir.
This method is correct. No problem is there. But sir, I have one request, sir. Sir, what if we have a need of 2 or 3 graphs in a single graph for fixed values of n in loop?
I
Am I
don't get
audible?
you. I don't get your question. Please
Suppose
repeat.
if it is suppose if it is simultaneous differential equations, we need to construct multiple graphs. By that time, how to proceed?
Yes, sir. Yes, sir. For fixed values, I can suppose if we have to plot the graphs for n is equal to 1, n is equal to 3, and n is equal to 4 for different values of n, how can we do that? You got my question, sir?
You want to say multiple graph?
Yes, sir. Yes, sir.
Multiple graph for the system of equations or different equations?
No, no, sir.
For
The same
equation?
for the same example you are considering this time. If we have to plot the 3 graphs.
3 graphs. Okay.
3 graphs for obtaining by this method for n is equal to 200, n is equal to 100, and n is equal to 50.
Yes. It is possible. It is possible.
Yes, sir.
Yeah, it is possible, and we can do for the same. Okay. I will introduce this problem in the next tomorrow session.
Okay, sir. Okay, sir.
Yeah.
Thank you.
Yes, it is possible. It is possible.
Thank you, sir. Thank you.
Okay, so once again, I am sharing the screen. Thank you. Nice question which you put. Okay, if I will try now, it will waste our time. So first I will test all this, prepare the code, then it will be easy to present.
Okay, sir. No problem. Okay, sir. Thank you.
Yes. But thank you. You put your problem. Now we have the forward. So there is very less difference now. Yes. So the example at this place we have the same. Example is same. Okay. I did not write the statement. No issue. Okay. So here you can see this is the dy upon dt. Okay. We have dy upon dt is equal to minus ky. So the example here is also same as we do for the backward. Okay. And what about for the forward? We have only this is ti plus 1 and ti minus 1. Okay, so here we have yi and yi plus 1. This is h. So we will have dy upon dt will be equal to yi plus 1 minus yi upon h is equal to dy upon dt. Okay, and when you will simplify dy upon dt means f ti yi. Okay, so at this place what will be f ti and yi. When you will simplify, you will have this equation. You can see when you will simplify this expression, yi plus 1 will be equal to yi and plus h f ti and yi. Okay, so this is the code for in MATLAB will be this equation, and the other part need to discuss also. Yes, so we need to initialize the interval, starting interval. You can see is this is the initial point and this is the last point. Interval we have is 0 to 1. Okay, and the number of points we are choosing for the grid point 100, h will be equal to b minus a upon n, and you can choose the value of k is 2. You can manipulate, and this is the initial condition, same as we have in the last, and only the one example we apply all these 3 methods, backward, forward, and central. Okay, then after you can come here. So all the other part are same. Here we have the grid. These are the grid. points for t and y. So t will be equal to line space AB n plus 1, same as we do in the last example, y zeros, and here is the initial condition, and here is our loop. Only we are using here forward difference, okay, and which we already explained. And then after these are the statement to plot the graph, and quite easy. And when you will execute this sequence of statement, and you will find that we have very nice graph. Okay, so this is the graph corresponding to this method. And here also this is the only another way to write the code, but the method example are same. Example is same, and here is also the forward difference. So this is our main equation. Yn plus 1 is equal to yn plus h minus k yn. Okay, and here is loop for t vector also. Okay, and at this place we are initializing the t and y both, and when you will execute, we have the same graph, and this is the another way. So you can check all these very carefully, and the values are same. Okay, and when you will execute, we have the same graph. So the method is same, but the way to write is different. Okay, and if you want to check the user defined function, that also I try to create in a separate file. Okay, all the content will be uploaded for you. I need to select all these three files, then enter. Yes, so here is our differential equation. We are choosing here x square plus y. Okay, and here is the same forward difference method. Okay, and the entire code you can see. This is the important part for us. Okay, yi plus 1 is equal to yi plus hf xi yi. Okay, and here are the numerical results. These are the values to the parameter a, b, y naught, h. Okay, and then we get the numerical values corresponding to x and y both, and then we will plot the graph. So at this place we call the function which we create for forward difference method, which is the files are stored at this place. Okay, and all these file which I prepared for you will be uploaded, share with you. Okay, yes, you can see the graph are the same. Okay, so I think there is no doubt in this method, because many things are same. And then after we have the last one, central. Okay, this is the central. Okay. Here is dy upon dx. No. This one not. Okay, so first we need to visit here. I want to open. Yeah, this is the finite difference method for first ODE, and is central difference. Yes, see here. Okay, so dy upon dx will be written as in this way. So what is about this one? We have this is xi. Here is xi plus 1, and here is xi minus 1. This difference is h, this is also h, and suppose that this is the curve. Here is yi minus 1, and here is yi plus 1. Okay, so when we will choose this interval, for this interval from xi minus 1 to xi plus 1, we have dy upon dx is equal to yi plus 1 minus yi minus 1 upon the length of the interval, which is 2h. H plus h, 2h. Okay, for this interval, the length of the interval is 2h. So that's why we have 2h. dy upon dx will be in this way. And after that, the application part will be quite simple. Sorry. Okay, yes. So here, the given function can be discretized following the same. Xi is equal to x naught plus ih. And the above problem can be written as in this way: yi plus 1 minus yi minus 1 upon 2h f xi yi. Okay, and we will solve for yi plus 1, and when you will solve yi plus 1, this will be equal to this one. Yi plus 1 will be equal to yi minus 1 plus 2h f xi yi. Okay, now we need to apply this method to get the value of yi plus 1. Now come to in MATLAB. Actually, in the case of central, just 1 minute. 1 minute, please. In the case of central, the same central method can be expressed as in this way. You can see. Yeah, see this equation. See this part. Dy upon dt at tn plus 1 approximate to yn plus 1 minus yn upon delta t, and the f tn plus 1 by 2 and yn plus 1 by 2 or f n plus 1 by 2. Okay, so the same expression can be written as in this way. So here is tn, here is tn plus 1, and here is tn plus 1 by 2. Okay, so this approach is used here in the MATLAB. See, yi plus 1. Yi plus 1 is equal to yi plus h, and you can see ti plus 0.5 into h. Okay, that is because of 1 by 2. Okay, and yi plus 0.5 h f ti yi. Actually, we need the value corresponding to ti plus 0.5 h. Okay, and at this place we are using, you can use Euler method. So by using the Euler method, this is the value corresponding to ti plus 0.5 h. Okay, so here the same method is implemented, and the other things are same. We are taking a is equal to 0, b equal to 1, n equal to 100, h will be equal to b minus a upon n, k equal to 2, y naught, and this is the f function. Okay, and the line space, zeros, other parts are same. So only we need to convert the central difference in this format, which can be easily used. Okay, there are several ways to convert in the central difference approximation. That's why I choose this example, so that we can easily convert the expression in this way to implement central difference approximation. And now we can implement execute this sequence of statement, and when we will execute, we have the same graph. You can see we have the same graph because example is the same. So by using forward, backward, and central, we can easily compare the same example by choosing the values of k and the other parameters. Okay, so this is the way to implement central difference. So this is all about this finite difference approach to solve these examples, to solve ordinary differential equations. Okay, any question, please, related to this example? Only keep in mind this value. This value is corresponding to this point, okay, which will be this one. And when you will execute, we have the corresponding graph. Now, there are some more examples for using the central difference, but it required some time to convert these equations. Okay, you can see here is also the central difference, but the way is different. Okay, but when you will try this example, first one and second example, then you need some more energy to implement here. Sorry, this is related to the forward. Sorry, this is the same method. Okay, come to in this file. Yes, this one. So this is also the central difference, but the way to compute or implement the method is different. Okay, see here dy dx is equal to 0s 1 to n, and dy dx is equal to y2 minus y1 upon dx. By using the forward at the first point, then we have the central difference. dy dxi is equal to this is the yi plus 1, and this is the yi minus 1 upon 2h or 2 dx. Okay, and then you will again use get the dy upon dx and by using the backward difference at the last point. Okay, so this is for the first point, this is for the last point, and these are the mid values. Okay, and then you can have initialize at this point to get all the values corresponding to each point, what we have the t vector, okay, corresponding to this line space. We need to calculate all the points y0, y1, y2, y3, and so on up to yn. So just keep in mind, at the first point, we will use forward difference, and for the end point, we are using backward. Okay, and for other points which are lies between initial and last point, we are using central difference. And then we will use Euler method to combine all these values. Okay, and here then after we can plot the graph of the given differential equation, and you can execute. We have the same graph. Okay, so there are various ways to implement this central difference, but the thing is, again, we need to understand the syntax of each and in which manner we can implement to get the values. Okay, so this will, I think the content which I tried to present here will help you to understand all this finite difference method, and also this approach will help you to solve partial differential equations. Once you are able to implement to finite difference technique or method for ODE, then we can use the same for PDE. Okay, so this is all about today's session, and I hope that very informative and knowledgeable things we discuss. Still, if you have any question, please over to you, and I will try to justify your question.
Excuse me, sir.
Yes, sir.
Am I audible, sir?
You are perfect audible.
Thank you, sir. Yeah, sir, may you go, please, any user-defined function, sir, please?
Pardon?
Sir, may you go, please, sir, you discussed three methods, sir.
Yeah,
Sir, there was one user-defined program, sir.
yeah.
Sir, may you go, please, to that very program, sir? I have a little bit confusion there.
Why we create a user defined?
No, sir. In user-defined function, in user-defined program, I have a little bit confusion. If you, sir, share that slide, that only I will tell you, sir, that confusion.
Your question is not clear to me.
सर मेरे कहने का मतलब है जो ये यूजर डिफाइंड प्रोग्राम आप अभी सर डिस्कस किए ना सर, इन तीनों मेथड में से एक फार्म,
हाँ,
सर प्लीज आप उस यूजर डिफाइंड प्रोग्राम को एक बार सर प्लीज शेयर कीजिए.
okay, I am sharing my screen.
ओके, थैंक यू सर, थैंक यू.
Yes, and okay, I think here is user defined. Yeah,
यस सर, ये
okay,
यस सर,
and okay, yes.
हियर ऑनली सर.
So this is the differential equation.
जी सर, इन नम रिजल्ट सर, आप नम रिजल्ट्स में जाइए सर. नम रिजल्ट्स जो है, नम रिजल्ट्स.
My ODE. This is the function of the differential equation.
यस सर,
You
आई
can-
गॉट दिस.
Okay, and dy upon dx is equal to x square plus y. You can take any equation at this place.
श्योर
Okay.
सर, आई गॉट दिस.
And this is the forward difference method. And
श्योर सर, आई
once,
गॉट दिस.
once you will write this method, okay.
And
you
num
will
result is
write it. Yeah, and here
Yes.
are the results.
Here only, sir. Here only. Sir, it is necessary to, while calling the function, it is necessary to use @myod
Okay.
at the
If you
rate.
will do, if you will do in this way and check
Okay,
what
sir.
happened. Check what happened.
There is nothing comes.
See.
Yeah, sir. This was
Okay.
my problem, sir. That's why. Yes, sir. I got. Same problem was in my program. Yes, sir.
Okay.
Thank you, sir. Thank you.
Okay.
Thank you, sir. Thank you.
Okay. Yes.
Thank you, sir.
Now
Thank you.
Okay.
Sorry for interfering, sir. Again, sorry.
No problem. This is very important to discuss all these things if you have question, because Actually, the thing is that when you are trying this code, you must break all this. Okay, when you will break this code, if you have some idea, if I will write, if I will remove this one, or if I will try to write in other way, then what happen? Okay, you must break and you rewrite yourself. Then this will increase your learning. Okay. Gangtak Nanpan raised hand. Yes, you can unmute your mic. Gangtak
Okay, greetings,
Nanpan.
sir.
Yeah, good evening. How are you?
I'm fine, sir.
Great. Can you please open your webcam? I want to see.
Okay, sir.
I want to see you.
Okay, sir.
You are from Nigeria.
Yes, sir.
Yeah. Your name is very familiar to me. Great.
Okay, sir.
Yeah, great. How are you?
Fine, sir.
Yes, please.
Okay.